All right, so section 1.1 is on patterns and inductive reasoning. So a conjecture, so if you hear the word conjecture in geometry, it just means a conclusion that you reach using inductive reasoning. And inductive reasoning is just reasoning based on patterns you observe. So basically, we're going to see a certain pattern, and then we're going to make a guess, which is a conjecture, on what's happening with that pattern. Are you pretty good with patterns? Have you guys done patterns since you were like in preschool? I feel like my kids do patterns like A, B, A, B, A, B. So some of these are pretty easy. Some are a little bit harder. So there's 3 stages of reasoning in geometry. So we look for a pattern, we make a conjecture, and we verify the conjecture. So when you look at this pattern, so we have 1 square, and then the next one we have 3 squares and 1 on top, right? And then we have 5 squares and 2 on top. So what do you guys think the next one would look like? How many would be on the bottom, and how many would be on top?
7 on the bottom, 3 on top.
Yep, exactly. So what are we doing to each side? Yep, we're adding 2 on the bottom and then 1 on the top, right? So we're basically adding 1 thing to the top, 1 thing to the right, 1 thing to the left. So it's going to look like that. Okay, and you can have different things like these. Like, have you seen the ones where they rotate? I always hated those ones. I had trouble with the rotating. I'd have to always turn my paper. So you can have some like that as well. So here's one like that. So can you guys tell how it's rotating? Would you say clockwise or counterclockwise? Do you guys see how it's kind of rotating this way? Okay, we're going like 90 degrees to the left, and then it's going around. So what will the next one look like? I think there will be 4 like that, right? And then where are the 2 going to be?
To the right.
Yeah, they're going to be on the right and kind of near the top, right? Do you guys see that? Like that. Those are the ones I always hated in school. I hated the rotation ones. All right, so number 3, it says predict the next 3 numbers. So we're going to look for patterns here. So if you feel like you know it, raise your hand. Am I going to have to call on you guys? It's just early. You're just not wanting to do this, huh? Okay, Sarah, what do you think? 3. And then what's the next 2 numbers? So we subtracted 2, we subtracted 3, we subtracted 4. She's saying the next one's going to be subtracting 5. So subtract 6 and subtract 7. So if we subtract 6, where will we be? Negative 3, And then if we subtract 7 from that? Negative 10, perfect. All right, so what are we doing on the next one? So we have 64, 16, 4, 1, 1/4. Rachel, what do you think? Yeah, we're dividing by 4. Okay, so dividing by 4, if I had 1/4 and I divide it into 4 pieces, that's a little tricky to think of. So dividing by 4 is the same as multiplying by 1/4. So really, we could think of this as multiplying by 1/4, multiplying by 1/4 each time. Does that make that easier? So 1/4, if I multiply by another 1/4, the next number would be 1/16. And if I take 1/16 and I multiply by 1/4, I'm going to be at 1/64. What about the next one? Anybody know 64 times 4? I do lots of mental math things. So if you're multiplying by 4, the easiest thing to do is multiply by 2 twice. So what's 64 times 2? 128. We all know that, right? You just kind of double it, add it to itself. What's 128 times 2? Yeah, 256. So it's going to be 1/256. All right, so the next one. So what are we doing here? Multiplying by or dividing by? Dividing by 3, right? Which is the same as multiplying by what fraction? 1/3. So if we had 16/9 and we multiply by a 1/3, the top is still 16. And the bottom becomes 27. And then we have 16/27 times 3, 81. And then 16/, anybody know that one? 81 times 3? Sam, do you know it? Yeah, good. The easiest way to do that is think about 3 times 80, which is 240, right? And then 3 times 1, which is 3, and then add those together. It's like the distributive property. So you're thinking about it like this way. So 3 times 81 is 3 times 80 added to 3 times 1. All right, so how about the next one? This one is a tricky one. I find that my gifted students, my honor students, will always overlook this because they're just making it harder than it is. You guys never make things harder than it is, do you? Especially not in math class. Do you guys ever do that in a math problem? You're like, wow, I just did like 18 more steps than I needed to. Whoops. All right, so who can see the pattern on this one? Yeah, Jacob, what do you think? Kind of. Joe, is that kind of what you were going to say? Yeah, it's kind of like going up by twos, right? 4, 6, 8, 10, 12, 14, 16. But every number is positive, negative, positive, negative, positive, negative, right? So it's going to go 12 is positive, and then 14 is negative, and then 16 is positive. So yeah, Jacob said kind of like they're, I think he said going up by twos though. They're actually going up by fours. So if you ignore every other, going from 4 to 8, you add 4. And then going here, you subtract 4, which is kind of the same idea. So you're ignoring the ones in the middle though. All right. We'll skip this for now, but we'll do this in a second. So there can be patterns with, graphs as well. So these are some kind of cool patterns that I like. So it says the first steps to form something called the astrid and then the 4-petal flower. And you just start to follow a little pattern. So like the first one says connect the points 10 and 0, and then 0 and 1, and then negative 10 and 0, and 0 and 1, negative 10 and 0, and 0 and negative 1. And then you keep going, and it's like 9 and 0, 0 and 2. So you go down for one and up for the other, and it creates this kind of cool shape. So we'll try those in a little bit. All right, but I like these next ones. So examples of number tricks. I always thought these were so cool when I was a kid, and people used to trick me all the time with these. And I'd be like, whoa, how'd you know my number? Do you guys ever do these? Okay, so everybody pick a secret number. So go ahead and maybe write it on your page. You can use a calculator if you need it. Do you guys need a calculator or have a calculator? So I want you to go through the steps. So you're going to add the next highest number to it. So if you had like 343, you'd add 344. Then you're going to divide by 2. Oh wait, hang on, did I skip a step? Okay, so add the next highest number to it, add 9, and then divide by 2. I don't know if you guys need these. Subtract your secret number, and it says, what is your conjecture? Okay, so my guess is that every single one of you guys at the very end ended up with 5. Did you guys get 5 at the end? Isn't that weird? Doesn't matter what number you pick. Okay, so geometry is all about seeing these patterns. So maybe I would say at the end, what'd you guys all get? And you all say, we got 5. And it's proving the patterns. So we're going to show why this has to be true. So let's use some algebra. So if I'm picking any number, what's a way to write any number in math? X, okay? What if I add the next highest number to it? So what's 1 bigger than x? X plus 1. Then it says we're going to add 9. Then I'm going to take my whole result. I'm going to do all over 2. I'm going to take all of that and I'm going to subtract out my secret number x. So let's simplify this. So when I have x plus 1 plus 9, how can I write that so it's simple? Exactly, 2x plus 10, all over 2 minus x. So what do I get when I do 2x plus 10 all divided by 2? So So half of 2x plus 10. X plus 5, right? So I have x plus 5, and then I have minus x. So what do I always get? 5. So we just proved why that was true. Okay, so let's try it on the next one. So again, pick a secret number. And then we're going to add 5. Hit enter if you're using a calculator. We're going to multiply by 2. We're going to subtract 4, divide by 2, and then subtract that secret number. Okay, so what did you guys all get? Did you all get the same thing? You ready? I got 3. Did anybody else get 3? Did you all get 3? Okay, so let's see why it's true. So we pick our secret number, x. We add 5. Now I want to take that result and I want to multiply by 2. So this is a little bit tricky. So how do I take this whole thing and multiply by 2? Because I don't want to just do like a times 2 off to the side. Yeah, let's do those parentheses around it. And then let's do times 2 maybe out front. It could be on the side too. I never like it behind it though. It seems weird. All right, and then we subtract 4. We take our whole result and we divide by 2. And then we subtract our secret number. So it's looking like that. So 2 times the quantity of x plus 5, all minus 4, divided by 2, and then minus x. So we get 2x plus 10 minus 4 divided by 2 minus x. So when we have 2x plus 10 minus 4, that's going to be 2x plus 6 divided by 2 minus x. Do we see where this is going? So 2x plus 6 all divided by 2, we're going to have 2x plus 6. So I'm going to get x plus 3 and then minus x. So we end up getting 3 every time. Okay, so the next one's a little bit different. So it says pick a 3-digit number. Take that 3-digit number and multiply by 11. And then multiply by 91. You can use a calculator on this one for sure. It's a little bit hard to do. Yep. Okay. So Joe, what'd you get in the end? Did you do it? Scott, did you finish yours? What'd you get? 300,300. I'm gonna guess his number was 300. Sarkis, what'd you get? Sam?
100.
You guys are picking such boring numbers. I'm gonna guess you picked 100. Sarah, what'd you get? Oh, you had 100 originally. Did we do anything other than 100 or 300? Yeah.
I had 101.
101, 101. So yeah, okay, good. I did 156, so I had 156, 156. So what's our conjecture? If you pick 231, you're going to have 231, 231, right? So our conjecture is that it's our number written twice, right? So our conjecture is like, if we pick 145, our new number is 145,145. Or if we pick 267, our new number is 267,267. Okay. So what do you get when you do 11 times 91? So just 11 times 91. Yeah, we get 1001. So let's go back to our like mental math thing that we were talking about. So imagine I have a number, like 149, and I multiply by 1001. Wouldn't that be like 1,000 added to 1 in parentheses? What do you get when you do 149 times 1,000? 149,000, right? So that would be the part that's 149,000. But what about the 149 times 1? 149. Do you see why it works the way it does? Yeah, kind of cool, huh? All right, so a counterexample. So a counterexample is an example that proves a statement wrong. So sometimes you make guesses and your guesses aren't right. So a common one that I always show my Algebra 2 students is we talk about the pattern 1, 2, 4, ... If I leave that pattern like that, 1, 2, 4, there are several different things I could have as the pattern. So what's one guess as to the next number? So some of you guys might see it. What do you think? 16. 16? Oh, close. Maybe. Actually, that would work too. 2 to the 0, 2 to the 1, 2 to the 2. Oh, maybe not. So let's do 8. How about 8? Do you guys see how 8 would work? How'd you get 16? Maybe 16 does work. I don't know. So because you can multiply by 2. Is that what you're doing? Okay, so multiply by 2, multiply by 2. So 8 is the next one. What else could we have? 7. How'd you get 7? Yeah, because he did the addition route. So he said, well, I can add 1. I can add 2. The next one could be adding 3. Right? So there's different things that you could have there. So maybe you think that the next number is, let's say, 8. But then I prove you wrong by saying, oh, the next number is actually 7. That changes your pattern, right? So then you have to like look at it again and say, well, what is the pattern then? Okay, so a conjecture or a counterexample is an example that proves a conjecture or a guess wrong. So it says, show the conjecture is false by finding a counterexample. So the difference of two positive integers is always positive. Okay, so integers are numbers like 1, 2, 3, 4, but also like 0, -1, -2, -3. So I could take, 20 minus 8. 20 minus 8 is positive. I get 12, right? Can I subtract integers and get a negative result? Yeah, what could I do? 1 - 2. Yeah, exactly. I could do something as easy as 1 minus 2. Those are two integers. But it matters the order that I subtract them, right? 1 minus 2 gives me -1. So that would be a counterexample. So the next one, so it says for all real numbers x, the expression x squared is greater than or equal to x. So I could pick a number like 4, and if I do 4 squared is bigger than 4. So that doesn't work. That's not going to be a counterexample. We want to pick something where when we square it, it is smaller than the original number. Yeah, what do you think? 0? That's true. Oh, I did say greater than or equal to, though, didn't I? So maybe I should do greater than or equal to. So the expression x squared would still be greater than or equal to if it was 0, but that's a good thought. Does negatives work? I don't know. What about negative numbers? What if I took like -3 and I squared it? Is that still greater than or equal to -3? Yeah, that works. So that's not going to be a counterexample. What are other strange numbers? Yeah. Ah, yeah. What fraction do we want? 1/2. Let's do it. So 1/2. If we square it, what do we get? 1/4, right? 1/2 times 1/2 is 1/4. Is that greater than or equal to 1/2? No, it's not. So this is a counterexample. Okay, does that make sense? So sometimes you kind of have to go through a process. You've tried several different things until you're like, oh, that doesn't work. Okay. All right, so the next one. So it says complete the conjecture. So the sum of the first n odd positive integers is blank. Okay, so this is kind of a cool pattern. So what's the first odd positive integer? What's the first number that's odd positive in an integer? 1. Okay. So if I'm just adding 1, 1 added to nothing is 1, right? How about the first two odd ones? So 1 and 3, right? What do I get when I add them together? 4. And the next one is 1, 3, 5. What do I get when I add them together? 9. 1, 3, 5, and 7. 16. 1, 3, 5, 7, 9. 25. So I have these numbers 1, 4, 9, 16, 25. What's special about those numbers? It does go up by 3, 5, 7, 9. Let's look for another pattern now. Sarah, what do you think? Oh, yeah, they're perfect squares, yeah. Do you guys see it? So it's 1 squared, 2 squared, 3 squared, 4 squared. So if I had the first 6 odd positive integers, what do you think that number would be? 36. What if I had 7? 49. So the sum of the first n odd positive integers is n squared. So if I had 7, it's 7 squared. I don't know why I have the biggest blank ever for that. It's just n squared, right? Okay, so in the 1740s, a German mathematician named Christian Goldbach sent a letter to Leonard Euler that said he believed that every number greater than 2 can be written as a sum of 3 prime numbers. So at this time, it was a convention that 1 was considered a prime number. So we're going to consider 1 prime. We know that 1 is not prime, right? Do you guys all know that? 1's neither prime nor composite. So Euler later stated that after 1 was no longer considered prime, every even number greater than or equal to 4 can be expressed as a sum of 2 prime numbers. So no one has ever proven this so-called Goldbachs Conjecture, so they still attributed it to the first mathematician, and no one has ever found a counterexample. So however, all even numbers up to 4 times 10 to the 14th, think how big that is. That's 4 with 14 zeros after it. Every single even number all the way up to that. I don't know why I have you can't do 14 zeros with a comma where I put it, can you? So everything up to that has been proven to satisfy this conjecture. So we're going to find 10 numbers that satisfy Goldbach's conjecture. So every even number greater than or equal to 4. So let's start with 4. Can that be expressed as the sum of 2 prime numbers? Yeah, what prime numbers could I add together? 1 and 3. If I had 1 was a prime number. Okay, so Euler said that we're not going to consider 1 prime, so let's do 2 other numbers. 2 and 2. You can add 2 to itself. 2 is prime, right? So how about 5? 2 and 3. How about 6? 3 and 3. 7. Can't do 4 and 3. 4 is not prime. How about 2 and 5? 8. 5 and 3. 9. 10. 7 and 3. And you could do 5 and 5. Some of you said other things. Right, so 5 and 5. What about 11? It's hard at first, isn't it? It's like, wait a second, what else? Can't be 2 and 9. Can't be 3 and 8, right? Oh, that's not. Why am I doing this? You should have stopped me. Every even number. Man, I started with, so yeah, I can't do odd numbers, can I? The conjecture says even. Did 11 stop us in that? Okay, so let's do, so not that one, or that one. So how about 12, 14, 16, 18, 20. Is that 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 22. So this table, I want you guys to do 12, 14, and 16. The back table, you guys do 18 and 20. And you guys do 12, 20, and 22. What'd you get for 12? 6 and 6 didn't work. 7 and 5, right? He's like, man, I had one job. All right, 14. you guys also get 14? 7 and 7. 16. 11 and 5. Yeah, good. That's a hard one. Is there any other way to do that one? I don't know. All right, Jacob, what did you guys get for 18 and 20? 11 and 7. 20. 13 and 7. All right, and this last table, 22? 11 and 11, that works, right. Okay, so basically every single number all the way up to 4 times 10 to the 14th has been proven to be the sum of two prime numbers. Isn't that crazy? Like, you would think that it wouldn't be, but it is. Yeah, so crazy. All right, so we're going to stop there for a sec.